Okay, good morning, everybody. So today, as we mentioned last time, we start talking about value semantics, which was introduced to C++ with C++11, and people have been using it, and people have been talking highly about it. So we decided to talk about it too, because it looks like it is here to stay. So for this, let's revisit our the concepts of left and right values, L values and R values. As you know, in an assignment statement, anything that can happen on the left-hand side is an L value, and anything can happen on the R side could be an R value. Like this one is an L value, this x a plus 5 is an L value, R value, sorry. That was the definition. Usually on the left-hand side, you have the variable names, but in C++, these kind of stuff are okay too, because when you dereference a pointer, you get an L value, right? We know that too. But this is not valid. We know that, right? This is not good. Okay, this is not good, but this is okay. We know that, okay? And L value is an expression that refers to the memory location. So, the discussion of L values and R values are deeper than this, but we will not talk about them. As I said before, C++ is a very detailed language, and we are not going to touch every aspect of it. This course is not about C++. This course is about object-oriented programming. Since our best case for the object-oriented programming language is C++ for this course, from time to time we looked at these kind of details, okay, and move semantics is one of them. The other one that I am not going to talk about is the lambda expressions. Lambda expressions, okay. So those are again introduced to C++ in C++11, but I am not going to talk about them because I mean they are nice, they are very useful, writing nice software, but I am not going to associate them with object-oriented programming for now, so I am not going to talk about them, but I strongly urge you to look at this lambda expressions. They are not that difficult. They are easy, and they are very convenient to use for some. They are like function pointers, but more convenient than function pointers. So let's go back to the left value, R value stuff. Is that going to make that sound? Just maybe shut the window or open it completely, maybe. Okay. Okay, so the green stuff are the R values, the blue stuff is the L values. We know that, and I can do this kind of stuff. So it is no surprise that if I am returning a reference, I can assign a value to reference. If I am returning a pointer, I can dereference it and assign a pointer to it. Okay, so these are the types of L values that kind of might seem like a surprising statement especially for this statement, right? It might be a surprising statement especially for the people from other languages and etc. Okay. And so we did that, okay, we said that I guess the value of f, no problem. P gets the value of what? Whatever f return. Well, actually, this is not that bad, but I mean, you know what it's trying to do, right? F is returning an integer, and I'm trying to take that integer, address of that integer, and assign it to p. That's not going to work. And this will not work because f, whatever it is returning, this is not an L value, right? It's an R value. It's an R value. So this one and this one will not work. Okay. So in C++ we have value semantics. What do we mean by value semantics? Suppose we have a statement like this, a string, for example. Okay, I add two strings, use the plus operation, which is used for catenation. Okay, then I add another one, another one, another one. So what's happening is the plus operator works on these two. It returns a temporary, and that temporary is added to this one. It returns another temporary. That temporary is added to this one, and etc. So the question is, what happens to these temporaries? Okay, since they are temporary, they will go away. But the idea is this: since they are regular string objects, they allocate memory, they keep their data in that memory, and when they die, they release that memory, and I am using that memory for something else. Okay, so the idea is, why don't we use that memory over and over again to make it more efficient? Okay, over and over again to make it more efficient. Why am I just deleting the allocated memory of that object instead of reusing again? That's what makes the C++ a little bit slower than the C language. Actually, in C language you can do this kind of stuff, reusing the already allocated memory, because there are no destructors, because there are no constructors. I can do whatever I want with my memory. But in C++, you have to create objects and you have to delete them. And if the object is temporary, then you have to do this over and all over again and again. Okay, again and again. That's not going to be a good thing. That's what we call value semantics, and this is what's happening actually. Okay, if I have a statement like this, an array, for example, or a string, A gets the value of B plus C plus D. Okay, and this is my plus operator. It takes two global plus operator. It takes two constant array objects. I make a temporary object which gets the value of left. There is one allocation and copying happening here, and then I do this plus assignment, another maybe more allocation and copying here. And when I return this result object, okay, after I return it, this object will be deleted, right? After returning it, this object will be deleted. So this is what's going to happen. I have B and C. They have their own memories, allocations in array or string, whatever. When it returns something, there is a temporary, and it is returned, and it is that I have this temporary. Then I use this temporary to make another temporary to add to the. Remember, this is B, C, and D. Okay, another temporary, and then I assign this temporary to this place. Okay, so the thing is that I didn't have to make these two temporaries. I could have done that without making those temporaries, and I could have put everything inside this result A, but that's going to be kind of difficult. So the idea is this: when you make this temporary, don't let it die, especially the dynamically allocated part of it. Reuse it over and over again. That's called the move semantics. With the move semantics, that's what we are doing. Okay. First of all, we need to make when we do this, B plus C plus D. Okay. I make a new temporary. I have to do this. Otherwise, where am I going to put the result? I don't have any space. Okay, and then after that I add this one with this one, but I use the position of this one, memory of this one, to keep my destination. And then finally I say my A that this is your memory location. Okay, so I didn't use any temporaries, and I am fine now. I am not using any more space. So to achieve this picture, that's what we are going to do. This is what we are going to do. That's what we are going to do to achieve this. This is our regular plus operator that takes two references, array references. It makes a temporary. I have to make it temporary. But after that, I have this function. This function says that, this function, okay, another function. This function says that I am going to take, okay, an R value and an L value, okay, R value and an L value, but this is a constant. Well, it could be a L value if it is not a constant. Here is what I am doing here. It is left plus assignment right. So I am using the memory of left to add right to it, and I am returning left. So what happened to the left? Well, left is going to be, left was supposed to be an R value, and it's going to go away. Okay, so that's the logic of it. And when I do this again, one more time, that's what I am going to do. So this means that this will take an R value. Okay, R value. What is an R value? A plus B returns an R value. Okay, this is an L value, but A plus B is an R value. A function that returns an object F, it returns an R value. Okay, so I can use this. For example, this is possible. F, whatever it returns, plus B. Okay, for this expression, this operator plus will work because F returns an R value. Okay, whatever F returns, we know that it's going to be deleted. It's a temporary. So instead of deleting it, I am using its position, I am using its memory to store more data to it, and I am returning it later. Okay, and it returns another R value. If it's going to be deleted, yeah, deleted. If it is not going to be deleted, then it's going to be used as an R value. That's what the meaning of move semantics is. So it makes things a little bit more efficient, especially when you are returning stuff from the functions, or especially you are dealing with the temporary objects. Okay, and that's the notation. Okay, let's move on a little bit, and this will be more clearer. Okay, in order to make our classes work with the R values, this is what we add. We add two more standard functions. This is called copy constructor. We know that. Okay, let's say this is an array. Okay, very simple array. I have a double pointer, and I think we forgot about the size, maybe, but we are going to ignore it. Okay, this is called the copy constructor. This is called the assignment operator. We know that, right? Now we are adding this. This is called the move constructor. Move constructor is used to copy a temporary objects or R value objects data to my object, and I know that whatever I am copying from is going to die soon, so I can take its memory position, I can take its resources. Okay, and move assignment it works exactly the same way. It says that if I am going to do this, if A is an array, and if I am doing this, if F is returning an array object, okay, this is an assignment, right? This assignment is now this assignment, move assignment, because F returns an R value, okay? It's not an L value. This is an, okay, this one is this green stuff, and this one is the black stuff. Okay, or why don't I use the correct colors? Yeah, I have the colors. This red one is the, yeah, this one, and black one is this one. If I can make the arrow. Okay, good. So, and this operator, okay, operator plus, okay, it says that, okay, I'm going to take just two objects of L values, constant L values. This one takes that. On the right side, it could be an L value, because for the temporaries, I am going to do this. Okay, so let's look at this picture. Actually, this is good. We have already did this. Okay, this one takes an L value reference L value. Okay, this one takes a constant reference L value. This one takes a R value. Okay, R value reference. We have never seen this, and we said that for this kind of stuff we were using this one. L value, R value didn't matter for us. Now I can make this difference. I can make this distinction. if I have an object x like this, okay, a function returns an x. When you do this, okay, x, since x is an L value, this is going to call this one, but this one returns an R value. This is going to call this one, okay. So the compiler makes it available for you to make this distinction. I can overload your functions depending on our L values and R values, and it is up to you how you implement those functions, okay. You can implement those functions in a way that they are exactly the same, or you can implement those functions in a way that this one knows that this x is going to go away because it's an R value, okay, because it's going to go away. Don't get confused about R values and the constant L values. Constant L values are different than R values, okay? So we are talking about function returns or the temporary objects, okay? Good. Let me move on to, I think I found some good blog post somewhere, and that guy is, where is my, yeah, let me go to my slides. I think I made these all available. Yeah, let me look at this one. Yeah, I think I got this from somewhere off the web. Where is it? Where is it? I think it is on, yeah, C programming tutorials or something like that. Let me open the okay. This series is good, by the way, okay. This guy, Alex, he talks about C++ 11 additions to the language. Okay, this one talks about the constant expressions, which is a good way of making your programs faster. And now we are talking about move semantics. Okay, instead of using this, or maybe I can do that too. Okay, good. Okay, let me open it in both ways. I cannot write on this one, but I could. Okay, good. Okay. Okay, so this guy is implementing. Okay, let's look at these. A gets the value of 1. A is an L value. Here, X is a global. This XREF returns this X as an reference. Okay, when you say getRef, it returns a reference, and I can assign 4 to it. Is an getRef is an L value, to it returns an L value too. How about this one? How about this one? Global X, get value returns the X. Okay, this one is returning what? This get value is returning a L value and R value. Yes, it returns an R value because I cannot assign a value to it. And similarly, this one returns an R value to a get name, get value, get name. Okay, I can make this assignment, no problem. Get name is returning an R value. Okay, and how do you detect the okay, how do you detect the R value detecting temporary objects that are not R values? Okay, this one is okay because I am returning an R value and I am keeping a constant reference to it. You might say that, well, it's a R value, how do you keep a, well, it's a constant reference, so it is okay, but this not is okay. You cannot keep a reference to an R value, not okay. We know that, so this definitely returns an R value. These two both are okay. Interesting stuff, but remember, get name returns a R value, and you can now keep a reference to an R value, okay? Because this is an R value reference. Name is an R value reference, okay? Name is an R value reference. What kind of things can I do with this? Well, it depends on, I mean, especially if you think about the bad things that you can do about this, the possibilities are endless. That's why it is a little bit dangerous, because it's a value that's going to go away, but it is possible. So these two examples are just for the sake of examples. We never use the references this way. If I have the name of the object, why do I keep a reference to it? But these kind of things are possible. I am going to do this now. Okay. So this one takes a reference, and it just prints the reference string out. This one takes a reference to an R value, reference to an L value, reference to an R value. Okay. Both of them are print reference overloaded. So I can overload them with respect to the reference, L value reference, and R value reference. Okay. So let's look at this one. Yeah. Okay. Good. So this is string me Alex, that guy Alex. Okay. Print reference and print reference. Which one do you think that this one will call and this one will call? The print reference me, Alex, will call which one? R value, L value print reference, or R value print reference? Let's go there. Which one? Okay. I am trying to hide this part, but I cannot do that. Anyway, okay. Don't read this green stuff, okay? So it looks like print reference me calls the first, it means, okay? It will call the first. This one will call the second. Why? Because me is an L value, and L value reference is this, okay? Get name returns a string, but it's an R value, it will call this one. Okay? So I can differentiate between those. I still didn't say anything useful. I am just telling you which one is going to call which one. Remember the trick that we played with the plus operator? Plus operator. The compiler told you that if you are calling the pre-increment operator, I am going to call a unary function. But if you are going to use the post-increment operator, I am going to call a binary function, so I can differentiate between them. Now the compiler is telling me that, okay, I can differentiate between these two functions, okay. For the L values, I am going to call this one. For the R values, I am going to call this one. That's what it says, okay. That's what it says. So again, it is up to me. It is up to me what I would do inside these functions. What I would do inside this function. And similarly, let me get rid of, okay, similarly, okay, for this class, for the L value objects, if I am making a copy, I am going to use this copy constructor. For the R value objects, I am going to use this copy constructor. I know that the R value objects will go away, so in this copy constructor, I can behave more efficient, okay. For the assignment operator, I know that this is going to be the R value. I can write more efficient code for that one. Okay, that's what we are trying to do. Still, we didn't do anything useful yet. I'm just trying to tell you what L values and R values and how we can differentiate in C++ 11. Okay, and let's write our array wrapper class. Array wrapper class is going to be just a simple array. Okay, like this. I have pointer integer array size, very simple stuff. And this is our regular class. I have a constructor. Inside the constructor, when I get this number n, I make a new array. I keep a pointer to it, p values, and size is n. This is my copy constructor, okay? Copy constructor takes constant array wrapper and other, okay? and then p values gets the, let me go to the, because these are just missing stuff. Okay, let me go to the proper code itself. Yeah, okay, here it is. Okay, so this is just a regular copy constructor, array wrapper, other. I make new space, okay, and I assign it to my size and copy the elements of the other one by one. This is what we did before. This is what we have seen before, right? And this is the destructor, array wrapper. Okay, and that's it. That's it. Okay. So this was what it used to be. We didn't use any R values or move semantics at all, and if we like to change this class so that it uses these temporary objects, this is what I'm going to do. Constructors, they are no different, and this is my move constructor. Let me put both move constructor and the copy constructor in the same slide. Compiler tells me that I am going to make it different for you. Okay, these are two different constructors. One is copy constructor, one is move constructor. If you are copying an object that can be an L value, I will call this one. But if there is an R value that you are copying, I am going to call this one. It is up to you, whatever you do. Look at the implementation of move constructor. What does it do? It says that I am not going to make new space for me now, because I am going to steal. It is literally stealing the other objects pointer and making a shallow copy, actually, right? It's making a shallow copy. I am making a shallow copy of the other object and including the size. I know that after I am done, the other object will go away, right? So I am making it ready for to die. I set it as p values to null, because when it's going away, it's going to delete its p values, right? So, but I copied it. I don't want it in a bad situation, because my object, my allocated space would go if I don't do that. So I am assigning null to the others p val, and other objects size is 0. Okay, maybe I didn't have to do the second one, but it is nice to have it. I don't do that kind of stuff with my copy constructor, because my copy constructor promises that I am not going to make any changes in the other object. Okay, so move constructor says that I am going to work on R value, I am going to work on constant L value. Good. Destructor is the same thing. Just delete the p values. Maybe I should have said if, well, I cannot write on this one. If p value is not null, then if p value, okay, yeah, if p vals not equal to null pointer, then do this. Okay, so that's going to be it. Let's see if I can. Okay, this is my copy constructor. That one. Okay. Let me go to the other slides, and I'm going to show you something else now. Okay, we talked about this. R value. This picture is important. Okay. These are the three things I can take an R value, L value, or constant L value, and nothing else. Can you think of any other type of object that you can get for F? I mean, in terms of X objects? No. Okay. Note that we don't have literals for the class types. I mean, there are integers. I mean, this is an integer. I is an integer. Okay, this is a literal constant integer. Literal constants are only available for the fundamental types, right? We have doubles, we have the floats, we have the integer, we have the characters, etc. You don't have literal constant string. Sorry, that was a wrong example. You don't have a string constant money, for example. You don't have a string constant, literal constant vector. You don't have it. You don't have literal constant linked list. You don't have it, right? So it has to be either an L value or R value or a constant L value. So one of them, either one of them. And the language says that I am going to make that distinction for you. It is up to you how you implement your functions. Okay? It is up to you how you implement your functions. Good. Okay? If you don't implement the second overload reference of an R value, okay, of course in that case the first one will be taken. The first one will be used by your code, and we are going to talk about it in a few minutes. Okay, so these are good stuff. Instead of copying, it steals the resources. Okay, that's what the move semantics is all about. It is stealing the other objects resources instead of copying them. Okay, and we leave the other objects in a destructible state. That means that the other object is still a valid object, but it can be destroyed without taking away all of my resources. Okay, and now my rule of 3 becomes rule of 5. Big 3 is now big 5. Well, but this big 5 is not as big as big 3, because if you don't implement big 3 when it is needed, you are in trouble, right? Your program will work wrong, will work not correct, will not work correctly. Why? Because whenever you do call by value with your objects, your copy constructor is not properly implemented. You will cause memory leak, or worse, you are going to make your customer's code crash. That's going to be a bad thing. But if you don't implement big 5, if you keep only big 3, if you don't implement big 5, all you are going to lose is some performance. Okay, that's what we have been doing so far. So we have not been bad things. Okay, the only thing is that our code is a little bit slow in terms of handling these kind of temporary objects. Okay. By the way, all the standard template library functions and classes, they implemented this move semantics. So without you knowing it, you have been using the move semantics with your vector classes or list classes or whatever class you have used. Okay, so we have been using them, but you didn't know that. So they are already working efficiently if the classes support those move semantics. Okay, so for the reverse compatibility, if we implement the old style member function with the big 3 rules, with L value reference, but do not implement the R value reference overloading versions, we keep the old behavior, no problems. If you like, you can move gradually to the move semantics. But if we implement only R value operations, we cannot call on these on L values. Okay, so you cannot say I'm going to do big 2 now. I'm going to do just R value reference values, the move copy constructor and move constructor and the move assignment. You just cannot overload those two. Once you start overloading those move assignment and move copy, move assignment, then you will have to overload all of them. Okay, so some good performance gain, they say. Other than some, we are going to look at this one in a few minutes. Okay, any questions so far? Any questions so far? Okay, so I showed you how to differentiate between L values and R values, just putting one more ampersand in it. And I showed you how to write a useful array wrapper class to do this stuff. And let's move a little bit more and let's try to see this guy's code. By the way, I got these slides from this guy. I even don't know his or her name, how to pronounce it correctly. It must be Zoltan, right? I don't know. So whoever you are, thank you. Okay, let's look at this class now. I have this class X, the same thing again. I have the copy constructor and move constructor. assignment operator, okay, move assignment, okay. So they call this copy assignment, move assignment. Okay, copy constructor, move constructor. Okay, let's try to see what kind of things are different between the copy assignment and the move assignment. Okay, copy assignment says that, okay, both of them will return the reference list, but copy assignment says that free all resources of mine, then, well, it looks like his English is mine too, so then, this has to be then, it's not that, okay, you have that. Okay. Free all resources, then allocate and copy resources from right hand side, right? That's what we have been doing. I free my old resources, then allocate some new resources and copy whatever the right hand side offers to me. But this move assignment says that I am going to free my old resources, but I am not going to allocate new space for me now. I am going to steal those resources from the right hand side, okay? Because right hand side is going to die in a few minutes. That's the move assignment operator, and it's going to be very fast for these kind of cases. Why? Because f is returning an object of x. Okay, whatever it is returning is going to die soon. Before it dies, I take its resources using this assignment operator, but this assignment operator is this one. Okay, this assignment operator is this one, it is not this one. Okay, good. So these are some of the rules of the, remember our rules for generation of the default copy constructor, default assignment. What was the rule? If you don't write a copy constructor, one will be written for you, and the default behavior of it will be the shallow copy, right? It will do the member-wise copy of the object. If you don't write the assignment operator, one will be generated for you, and the default behavior of that assignment operator is going to be the member-wise copy again. We don't like those are the rules. So these are some new rules. The two copy operations, copy constructor and copy assignment, are old operators, are independent. Okay, declaring a copy constructor does not prevent compiler from generating copy assignment and vice versa. Okay, these are the rules of the C++ 98 or the previous rules. Okay, new rules: move operations are not independent. Okay, declare either prevents the compiler to generate the other one. If you don't declare anything, if you have a class like this, remember what I said, the class that I like most, class A, this one. Okay, this one has in C++ 11, this one has a copy constructor, an assignment operator, okay, a move constructor, and move assignment, and destructor defined. Okay, they are all defined for this one. They are all defined this one. But the rule says that if you declare one of the move operators, move constructor or move assignment, the other one will not be generated for you. That's the rule. Okay. Rule number 3. Okay. If any of the copy operations declared, that is the copy constructor or the copy assignment, none of the move operations will be generated. A new rule. And just the opposite is the true. If I could have said and vice versa, and vice versa. Okay. If any of the move operation is declared, okay, then none of the copy operation will be generated. Again, these are new rules. If a destructor is declared, then none of the move operations will be generated. Okay. So, I mean, so far, remember the first classes that we wrote? Day of year classes. We didn't define any copy constructors or the assignments because they were okay. So that means that we didn't write any copy constructor, copy assignment, or destructor. Well, in that case, for those classes, the move constructor and the move assignment were defined by the compiler, and your objects are fine. they will work very efficiently in terms of making those kind of assignments. Or your objects will work very efficiently in terms of using them with the vector class, because vector class takes advantage of move semantics. Okay. Good. Let me move on. This guy has a few good examples. Okay, for reverse compatibility, move operations are generated only when no copy operations, no move operations, no destructor is declared. Okay, so think about our original day of year class, our original, maybe your first class that you have written, your class about the solitaire, tag solitaire, that didn't have any destructors or the copy constructors, etc. So the move semantics work for your classes automatically. But as soon as you introduce one of the copy operations, copy constructor, assignment, or destructor, then those will go away. They are not declared anymore. Okay, a simple program, very simple program. Let's look at this one. It is going to be interesting. Yeah, well, structs are classes are, right? I mean, the main difference between a struct and a class is that everything inside a struct is automatically public. Everything in a class is by default private, right? So this is just a class. My constructor has a gets the value of plus plus count. Count is a static integer which is initialized to 0, and I have an astatic a. Okay. So what are we going to do now? I make a vector of s of 5, and I push back 1 s. So in this case, it looks like 5 constructors will be called here, right? And one more constructor. And what is the output of this program now? What is the output of this program? It's going to be, because 5 of them will be created every time a new object is created, I increment the static value and I assign that value to a. So this will say that, okay, inside this one, it will print 1, 2, 3, 4, 5, and 6, right? That's what's going to be. That's good. I am not interested in what this for loop is going to print out. I am interested in this constructor being called and the move semantics. So I am going to make a little bit changes for this one. Okay. This is I am not sure if this is a real statement or not, released by the committee, C++ standard committee, but this is the fact of life for the C++ programmers. The C++ standards committee shall make no rule that prevents C++ programmers from shooting themselves in the foot. So dealing with these kind of move constructors and move assignment, sometimes it's dangerous. Sometimes they may, if not used properly, they may crash your program, may misbehaviors, etc. Similar to pointers, okay? Pointers are not that difficult, but if you are not careful, okay, they are going to hurt you. The same thing again here, okay? So this is what I am going here, okay? Don't make this a struct. Get this out, and good. Let's look at this code. Okay, so I have my regular no parameter constructor, copy constructor, okay, move constructor, copy assignment, move assignment, and each one has a printout statement in it so that I know which one is called. Okay, let's see. Let's start from the main function, and I have a swap function templated nice. It's going to swap the values of these two objects, okay, namely this A's. Okay, as A and as B, now I'm going to call to what? I am going to call to these will be my outputs, okay? I am going to call just two constructors, A and B, constructor 1 and constructor 2, right? Then I am going to call what? Swap AB. Since this is a copy, this is a reference, these are L value references, okay? No copy constructors will be called, no problem. When I come here though, so what's going to happen? Tell me. What am I going to print on the screen? T temp A. Is this going to be a copy constructor or move constructor? It's going to be a copy constructor. Why? A is a L value, right? So it's going to be a copy constructor. So these two will come from this line. This line will produce a copy constructor. So a copy constructor says copy CTR. Okay? That's going to be the copy CTR. Good. How about this assignment? A gets the value of B.
Copy assignment.
It's a copy assignment, right? Why? Because B is a L value. So it's an L value. Then I am going to call this. So this one will call copy assignment, and similarly this one will call copy assignment too. Copy assignment. So it looks like I'm not gaining anything. I mean, I know that T is a temporary, right? T is a temporary. Yeah, right? Sorry, temporary is a TMP is a temporary. TMP is a temporary. Still, yet I am not using any of its resources and etc. Which I don't like, but it looks like, I mean, the compiler cannot know that I am going to treat this TMP as a temporary, right? Compiler sees it as a regular L value object. So what am I going to do? Again, we are going to come back to this one. We are going to do something very dangerous, but if you are careful, then that's what we are going to do. We are going to tell the compiler that make this TMP an R value object. Okay, treat it as an R value object. Okay, for that we use this std move. Okay, we are going to do this. Treat this A as a R value object. Okay, treat this B as an R value object. Treat this TMP as an R value object. And if I do that, my code will be again constructor, then move constructor, move assignment, and move assignment. If you like, you can do. If you know what you are doing, this is possible too. So this is std move. Std move, it just changes type from L value to R value. It's like C, right? In C, I can force anything to be a void pointer, right? Just make it a void pointer. All the pointers could be a void pointer. If you know what you are doing, that's very useful for most of the time. But if you don't know what you are doing, that's going to be a trouble for you. Okay. Any questions so far? As I said, move semantics are nice. They are very useful for gaining performance in terms of temporary objects. And we have been talking about the temporary objects a lot. And if you have nicely written C++ 98 code, which doesn't include any of the big three in it, okay, then when you compile your code with the C++ 11, your code will be a lot faster. It's going to be a lot faster because the default meaning of the move constructor. Default meaning of the move constructor, by the way, is making a shallow copy between those. Okay, so that's going to be nice. That's going to be nice. Okay, good. Let's take 10 minutes of break. But yeah.
If we didn't define a move or
move assignment
semantics for the
yeah.
T, what happens? This throws an exception.
This one?
Yes.
Well, if you did not define anything, well, that's what would happen with our previous code. I mean, this copy constructor and the copy assignment will be called automatically. I mean, it doesn't matter previously, remember? This one previously calls our copy constructor, right? And this one calls our copy constructor too. Okay, if you don't define it, there are no R value references defined for us, so our default copy constructor will come in and work. So this will not have any effect. Okay, good. Let's take 15 minutes of break. 10:39. We will continue, and I will bring your attendance in a few minutes. Efendim?
Attendance dağıtmayı unuttunuz galiba. Yoklama kağıdı.
Getirdim, tamam.
Getirdin mi?
Ha. Okay, so let's look at this example now. Just because I made these A, B, and TMP write R value. For this one, copy constructor. For this one, for this one, move constructor. For this one, move assignment, and move assignment will be called. Okay. Again, the rule is this. What is the rule? Okay. I'm going to give you the opportunity, and if you like to shoot yourself in the foot, then you are free to do it, and you can do whatever you want. Sometimes this will be in a good way, sometimes you use it in a bad way. But if you are careful, if you are a good disciplined C++ programmer, all these features are nice features, and you can do whatever you want. Okay, so this is good. We did that already. Okay, so good. Do I have any other? Okay, so write value reference cast move, the meaning of it. Okay, it usually has a positive effect on performance, and many standard library functions utilize write value references. So when you think that this, for example, you have a, let's say, a vector of integers v100. Okay, you have such a vector, and I'm going to push that vector into the end of this vector number 2. Okay, push back, and I am going to do this v. And I know that I am not going to use this v anymore after this point. It's going to die. I am not going to use this v after that point. In that case, you may say move v. Okay? So treat this v as a R value. Okay? So you can steal its resources, because I am not going to use it after this point. Okay? Very dangerous thing, because after that, if you keep using v, you'll be in trouble, right? You'll be in trouble, but that way your vector v2 will not make any copies of it. We'll use it as an original. Okay, that's what it's going to do. Okay, so it's a again performance issue. If you like to do that, if you know what you are doing, you can always do that. Okay, you can always do that. And as I said before, let's look at the C++ vector reference of it. You are going to see that. Yeah, okay, C++ reference is a better source. Okay, so class vector, let me try to find, yeah, okay, these are the data members, these are the constructors, but why don't I see, let me go back to the C++com, because it has separate documentation for the C++11 and C++98. Yeah, okay. So this is C++98. Let's go to C++11. Okay. The constructor for the vector. Okay. I have 1, 2, 3, 4, 5, 6 constructors, and one of the constructors are the move constructors. Okay. So these classes, all these classes are modified so that they support these move operations. So if you have an R value available, it's going to take advantage of it. So if you are giving an R value to copy from, then this one is going to take advantage of it. Okay. As you asked, what's your name again? Onur. As Onur has asked, what happens if the class doesn't use the R value? I told them it's going to be always going to be the less less performing class, it's going to work fine, but it's going to be a little bit slower. That's it. Okay, go back here. So sometimes we had to use it. Again, maybe dangerous. A variable with name left with unspecified value could be, but that's our thing to that's our again, we are careful professional programmers, and we are going to take that risk because we know what we are doing. Okay, let's look at this example. This is going to be interesting too. What would you expect here? Okay, I would expect, okay, for this one, okay, for this one, there will be 5, right? There will be, for this one, there will be 5 constructors. Okay. For this one, there will be another constructor, S. But remember, remember the first rule of the object-oriented programming. We don't care what the class itself doing in it. All I care is I am pushing back one more element to the end of the vector, right? That's it. But the vector may be reallocating some space and moving things around. Okay, moving things around and doing that kind of stuff. Okay, so I am not sure, but if it is doing it, I am going to see what it is doing, because I placed all these stuff in here. Okay, if I am doing this by pushing back one more element to this vector, maybe it has to allocate more space, it has to copy all the old data to the new places, and etc. That's what I'm going to see in a few minutes. It looks like it is doing that, right? Okay, it is doing that. So I have come on, okay, I have 1 2 3 4 5 6 constructors, and there is a move constructor. Where is the move constructor coming from? Move constructor comes from this pushback, right? Because this pushback is going to take this one, and it says that, remember, this S returns an R value, it's going to go away, and this pushback is using it. Let's go to the pushback, actually, vector, and vector. Let's look at the definition of pushback. Let's see if it really takes a modifiers pushback. Okay, see, they overloaded it. It takes one constant value, constant reference, and the other one says that I'm going to take an R value, so it is efficient. You know what it does? It just steals the internals of whatever it is being pushed. Okay, so that's where it is coming from. So this one says that I'm going to take a constant, I'm going to take an R value reference, and that R value reference, okay, that R value reference will be taken by this pushback, and since pushback has to make a new object, it makes that object using this R value. Okay, that's that move comes from. But after that, I see 1 2 3 4 5. See, it makes 5 copy constructors. Why? Because it looks like this vector inside itself, it is moving things around. But why? How come it is not using our copy move assignment, or move constructor instead of copy constructor, right? So it is not. I expected that inside the vector it would use a move constructor instead of copy constructor. These are all coming from the pushback, right? So you would expect that. Well, there is a trick. The trick is this: if you promise that your move constructor doesn't throw any exceptions, you can satisfy this need. As I said, these are very detailed stuff. If you read about it, sometimes from some of the constructors there would be an exception coming. Okay, that's a very rare case. And if you promise that no exceptions is going to occur, no exceptions, if you run this is what you're going to get. These are all will be move constructors. Okay, so it's going to be very efficient for the. I mean, I am using a new class. I am defining all of these functions, and all of a sudden, if I write the things right, my vectors of class S will start working in an efficient way. Okay, that's what's happening here. That's what's happening here. Okay, so read about this no except. Well, no except means that this function will not throw any exceptions, but why it is making our moves work. Okay, it's a detailed stuff. I'm not going to go into it. As I said, some of the discussions have nothing to do with the C++ programming. In fact, move semantics doesn't have anything to do with the object-oriented programming, right? It is a detail of C++ programming. So I don't want to go into those kind of details. Just giving you some pointers. By the way, this series of, where is it? Yeah, this guy Alex's series of C++ new stuff is good, because after that he talks about what? Null pointer and strongly typed enums after that, and he talks about what? After that he talks about, where is the, okay, enumerations. After that, R value stuff. Previous, I think he talks about lambda expressions somewhere too. So read this whole series. Okay, let me, okay, generalize constant expressions, and before that I guess he's talking about yeah, range based for loops. We already talked about them. I didn't talk about them truly though. Okay, you already know this. I have a map or vector, doesn't matter. Okay, he's talking about it, and before that, yeah, lambda expressions are here, lambda functions. Just a simple iteration. Yeah, okay. So you are defining a function. This function is see out hello world, and you can call this function, okay, this is just a lambda, usage of the lambda, basic lambda syntax, and I am trying to here use it in a good way. So this one, and understandable stuff. Okay, you can freely return lambda functions. You can pass them as your, okay, so this is just a lambda function. You can pass them as your parameters and use them freely. Okay, and they have their own types. There is a new type called function, std function. Okay, since you treat your function now like an object, so object-oriented, all of the object-oriented rules kind of applies to these lambda functions, and that opens up a new world. So again, I'm not going to talk about it. So let me go back and let me try to see. Okay, next one, range-based for loop, and after that constant, and after that I guess I have my, yeah, R value reference. I think there is some interesting code at the end. We talked about this, and we, yep, okay. So remember our array wrapper. Now I have added this data in it. Okay, I have my pointer, integer pointer array. Okay, and I added some more data in it. Okay, metadata. Inside metadata, it doesn't matter what it is. I think it's just a added a simple string in it. Doesn't matter what it is, but it's just adding a new object to a composition. Okay, and this is my array wrapper now. My constructor with an integer. Move constructor is this. Okay, so the problem is going to be here is this. Okay, I am going to steal the other objects pointers, but when I am stealing the other objects metadata, which is a large object actually, I am doing a copy thing. This is a copy constructor call for the metadata, right? That's not a good thing, right? You understand what I'm saying here? I have two things in my object. One is a pointer. I can steal the pointer like this. I just steal the pointer, just copy it. So I know I got everything that the other object has. But when I get the when I get to the point of the metadata, which is a very large object, I am copying it now. This is which is inefficient. I don't like it because the meaning of move constructor is supposed to be fast, and I know that the other vehicle is going to die. So what am I gonna do? What's your solution? I just move this. Okay, I just make this a R value. Okay, so that's the thing. So I just move it. So other metadata becomes an R value. Now my move constructor for the metadata will work, and that will solve the problem. That will solve the problem. Okay. So the how the move work? Okay, STD move work is just a typecasting stuff. It is not expensive. Okay, it is just telling the compiler that, okay, believe me, this is an R value thing. If you are doing it right, then you should be fine. Okay, I guess that's it. Again, movable objects and STL containers. Standard library did everything, implemented all the stuff that I showed you. Okay, remember the pushback operation. It works with the move semantics, etc. And if you are concerned about performance of your objects, your classes, definitely implement the move constructors, move assignment operators, and for your functions, if you are getting some objects through reference, again, you can overload your functions with the move overloads. Remember pushback? Pushback is overloaded with move, overloaded with the R value references, L value and R value references. Okay, so well, you might say it's a lot of work, but if you want to be more efficient, then what you need to be. Good. Any questions about this move semantics? Did I miss anything? Yeah, I think these are all done. Yeah. Oh, by the way, this is a bad thing, right? You know that, right? If I am this is okay. If I make a local object and if I return the local object, you don't want to kill a local object inside the stack. That's going to create some problems for you. So be careful about this kind of stuff. Should you return or move? Okay, so this is called RVO problem again. Remember at the beginning it said that most of the time this is efficient, but for some of the RVO cases it's going to be problematic. Yeah, escape some rare RVO situations. So in that case there are some exceptions, but we are going to ignore it for now. Good. Any questions about move semantics? If there are no questions, then I will continue then with our new chapter, which is about standard template library. Okay, go there, and this is going to be the last chapter about C++. I am not claiming that I talked about all the aspects of C++, and I am not claiming that I talked about all the aspects of object-oriented programming. Many things that we need to talk about again will happen, and some of them we will talk about in Java. But this is a very large open world, and you are supposed to read it yourself. You are supposed to learn it yourself, especially the new additions to C++11. Read about the Lambda expressions. Read more about the range for loop, because that's more than we talked about. But so a standard template library, as we said before, is a templated library. It talks about vectors, and it talks about basic strings, linked lists, trees, maps, hash maps, and etc. We'll talk about it. We'll talk about three things. Iterators. Iterators are kind of generalized pointers. Okay. For for what we know about pointers, they work for the arrays, right? Very well. We talked about the arrays, and when you increment a pointer, it points to the next element inside the array, and etc. We like to generalize this feature so that it works with all kinds of containers. So iterators is that idea. Containers are STL classes. Vector is a container. Okay. List is a container, etc. We are going to talk about them. There are different types of containers. For example, adapter containers, container adapters. They are very simple but nice idea, you will see. And we have associative containers. And we'll talk about some algorithms, okay? There are some global functions, templated global functions. For example, a sort function or the search function, or for each function that will work all kinds of containers, and we'll talk about them. So let's talk about the iterators first, okay? Let's talk about iterators first. This code, you are familiar with this code. I have an array of size something, and I defined a pointer to the beginning of the array. From 0 to 10, I increment this index I, and I increment this pointer. And every time I print out the reference pointer. So I expect this will print out 1, 7, 10, 11, minus 10 on the screen, okay? I know this one. Let's say I have an list of integers, IV, okay? And I am doing this weird stuff. Can I do this? Of course, why not? Okay. I am taking the address of the beginning element. By the way, this notation may not be valid because there is no indexing with the list, but bear with me, right? Okay. So I just abused the notation a little bit. So 0 at the linked list element number 0, I take this address and I'm pointing to it with a pointer. I can do that, no problem. But if I try to do this, am I going to be in trouble? Because linked lists work this way, right? Okay, it says that, okay, 7 will be here, then there will be a pointer, it will point to next node, and there will be another pointer, it will point to another node, and etc. Okay, would this work? When you make this plus pt, this is crazy, right? It's not going, because this linked list is not an array. Okay, I don't know how they store their values in the memory, but I'm pretty sure that this will be a troublesome case for me if I do this plus pt. Okay, but I like this notation. I like to use pointers to point to the elements of the linked list or the array or the vector or the hash set or whatever container I have. Okay, that's the idea of the pointer. I like to generalize this idea of using pointers for any kind of containers. By the way, instead of making this a list, let's make this a vector. Would this work now? Would this work? Get the address of the first element inside the vector and increment this pointer to point to the elements of that vector. Do you think this would work?
No.
Well, the official answer is definitely no, but most of the time it's going to work because vectors, it's logical that they keep their elements as an array inside it, right? Well, it's going to work for most of the time, but you are not supposed to use it this way, okay? You are assuming that the vectors are using arrays to keep their elements inside it, but it's their business. I mean, they are not making any promises about it. Remember our vector of booleans? Remember those vector of booleans? It was a specialized class, right? If you do this plus plus for a boolean pointer, this will definitely not work. I can guarantee that, right? If I say boolean, vector of boolean, and if it is a boolean pointer, plus plus pt will point to the next boolean in an array, but it will be a byte away from the original one. Remember the boolean specialization of the vector class? Okay, they had written the boolean specialization in a way that it behaves more efficiently in terms of memory usage. They keep probably 8 booleans in a given character, in a given byte. So this will not work for the booleans. So that's definitely not question. That's definitely a bad thing. Okay, but I like to use this idea plus plus and dereferencing and the, so that's why they have invented these iterators. Okay, they have invented these iterators. Iterators are abstraction. Okay, they behave like the pointers, and the plus plus operator, minus minus operator works on them, and the square bracket indexing and the plus arithmetic operations with the iterators, they all work fine. So that's what we are going to look at. Okay. Each container has its own member function like this begin and end. This one will return a iterator. Remember, iterator is a specialized pointer. This one will return an iterator to the beginning of a vector or a set or a linked list or whatever you have, okay? And this is going to show you the end. Let's say, hypothetically, let's say this is my vector, okay? This begin will point to the beginning and will point to the end, okay? It is not this last one, it is and, okay? That's a pointer, 2 pointers. So if I can take a pointer to the beginning of the vector or linked list or whatever I have, okay, and I keep incrementing that pointer until it becomes end, then I should be fine. Let me show you one program like that, okay? And in fact, let me open my Dev C++ and let's see the actual code. What happened? Am I getting it? Yeah, there it is. Okay, let's open all the examples of this chapter number 19. Open all of them. Okay, number 1. I have a vector of integers. Okay, I added 4 integers in it, and this is my iterator. Okay, iterator, it looks like, why don't I make this like that? So okay, good. So type of P is an iterator, but iterator is an inner class inside the vector int. Okay, so all the classes, all the containers, they have their iterators defined as an inner class inside them. Okay, P gets the value of the container that begin. Container is my vector, and I will continue this if P is not equal to the container, and every time I increment P by 1, like the pointer increment, okay, and I dereference it and I print it out on the screen. So this one will print 1, 2, 3, 4, 5, 1, 2, 1, it's a 1, 2, 3, 4 on the screen, okay? And if we like, I can do the same again. container begin, container end, and I am assigning 0 to all of the elements using the dereferencing. Okay, whatever you can do generally, you can do the same thing with the whatever you can do generally with the pointers, you can do the same thing with the iterators. Okay, the only thing is that, okay, instead of saying, we used to say point to the beginning of the array, we used to get the address of the beginning of the array. Now we are saying, let's call this begin and call this end. That's what we are doing right now. The nice thing is, doesn't matter if it's a vector. Can I compile this? It is, yeah, okay, I'm compiling it. I compiled it, no problem. What did it say? Is not a namespace? Vector int, okay, I'm going to get this out. I'm going to compile this. I think it has compiled. Did we get any? Yeah, okay. It compiled, right? It compiled, and instead of making this a vector, I am going to make this a list. And of course, I need to copy this stuff and compile it. I did not include list, compile it. Well, I did not, I forgot to change this. Okay, how about this? Much better, right? I'm going to make this like that, okay, and how about, okay, and so I don't care what kind of type it has. I am going to do this. I compiled, and it compiled. So the point I am trying to make it is this. Doesn't matter if you are working on a list or a vector, this code will work. Okay, it will produce exactly the same thing. Vectors and linked lists are very different data structures. But to me, I abstracted their interfaces, I abstracted their structures. To me, it is the same thing if I like to start doing this kind of stuff. Okay, pushing back, running an iterator, running a pointer from beginning to the end, print them out or making them 0 and printing them out again. Okay, so again, if we come back to the stuff, okay, so the idea is to abstract away the details of these pointers and behave them like they are pointers that can work for any kind of STL container class. Okay, good. So, did I miss anything here? No, I don't think so. So, this one and this one is important. So, iterator is an inner class inside a vector, and it's a public class, of course. I declare objects of it, and each one has its own iterator. And by using this trick, by saying that auto, otherwise I had to say this is an list iterator, right? I didn't want to do that. I just auto p is container begin. Okay. Now it should make more sense for you to look at. Remember, I used to just whenever we see them, I used to just, okay, here it is. So begin and end, they are always defined for this kind of containers. Okay, and there is an R begin and R end where I am going to talk a little bit about them. This reverse begin and reverse end. Reverse begin starts from the reverse of the end of the array, where vector or list. R end is the reverse end, that is the beginning of the array. And it looks like they have added some constant iterators for the vectors in C++ 11. Okay, it looks like there is nothing that we did not cover, right, inside the vector class. All of them are there. So this is the vector bool. Okay, good. So let's go back to my slides. Kinds of iterators. Okay. These are all possible with the vector iterators. Let me show you the code itself actually. This is the code. Okay, this is a vector of characters. I push back A, B, C, D on it. I print them out one by one using the container. Or see, I have this iterator pointing to the beginning of the vector. Using the container index, I can get the second element. Using the iterator index, I can get the second element. Like the pointers. Like, as I said before, they behave like the pointers. They behave like the pointers. And this one behaves like the pointer. Okay? So this is okay. Plus, 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 minus, minus. Well, I'm not going to talk much about them. Let's look at this example now. What do we have? Reverse iterator, yeah. So I have ABC on a vector, and this iterator P is a forward iterator. I am assigning it to this begin and end, and increment it one by one. This one will print ABC. This reverse iterator, okay, it starts from the reverse R begin. Okay, so it is pointing to the end of the vector, and when you increment this reverse iterator, it is walking backwards. When you say plus plus, it walks backwards because it's the reverse. And this R and is actually the beginning of the array. Assuming that the forward iterator begin and reverse iterator R and are the same thing is not correct all the time. Sometimes it's correct, sometimes not. So if you are using the reverse iterator, always use R begin and R end. Don't use begin and end. Okay. So this one will print ABC first, then CBA next. Okay. So this is the reverse iterator. Okay, so this is about corking list. In C++ STL we have the class list, and list and vector are very similar, but there are differences. How can I compare them? Let me try to compare them by putting their, okay, this is a vector, and let me get the list is there. Okay, so this is a vector, this is a list. So see, list doesn't have a specialization for the booleans because it doesn't make sense making a list of booleans more efficient because they are not stored one after the other one. Okay, make this like that and make it like this. Do it again. Okay, tell me, whenever you see the difference, you just tell me the difference. Make it a little bigger. Bigger. Okay, so member functions, constructor operator assignment, they are all available. Capacity is, so vector capacity is more detailed. Size, max size, okay. Doesn't make any sense to have a capacity for the linked list because whenever you need to add something, you need a new node, right? Doesn't matter if you add it at the beginning or at the end. So capacity doesn't have it. Empty is their reserve, and shrink to fit are specialized functions for the vectors. Okay, element access, yeah, okay. See this one? For the element access, I have the index operator, at operator, front and back and data. For the list, you have only front and back. There is no random access for the list. If you like to reach the fifth element of it, you need to start from the beginning and iterate 5 times, right? That's expected. Okay, modifiers. It looks like Just a minute. Efendim? Tamam, ben alt kata gelebilir misiniz? Çıkışa. Tamam, oldu. Görüşürüz. Aha, çıkışta. Hı hı. Görüşürüz. I think I'm out of time and I am going to stop here. Somebody's expecting me outside. So we will continue doing the discussion on tomorrow, and I will finish up with the SDR. Next week, Java. Okay? See you next week.